Welcome to topology class. Today we will discuss about continuous functions. What do you mean by continuity? How we can define continuous functions? Like that we will discuss under this topic. This topic is coming under section 3, continuity. Continuity and related concepts. Continuity and related concepts. 3.1 definition. Let f from a topological space X to a topological space Y be a function and x naught belongs to X and script T and script U be topologies on X and Y respectively. Then f is said to be continuous or more precisely we will say that TU continuous at a point x naught if for every v belongs to U such that f of x belongs to V, there exists U in script T. This is script U. This one is simply U, right? U belongs to T such that x naught belongs to U, this U, and f of U is contained in V. F of U is contained in. So this is the definition. So let us examine the definition with real analysis. In your real analysis class, you have studied definition from real class. So what you studied in that? First you studied f from some xd to xd1 to yd2 is a function. Then x naught belongs to X, right? Then we will say that this is continuous at f if whenever we are considering an open set here, right? X, Y, is f. So how we will prove is, for x naught means we will prove if there exists an open set, right, which contain our f of x naught, then there should exist here, right? There should exist an open set here which containing your x naught. That was our definition. then we will say that this function f is continuous. In real case, you have taken many times. Here you take an open set and show that its image is again going to be an open set, right? That too you have shown. So what about here's definition? Here we are having the same criteria, right? So we'll say that open means it belongs to the topology. Now we examine here. So for every v belongs to u such that f of x naught belongs to v. That means every open set in y which containing f of x naught, right? There exists u belongs to t. U means here's open set. Something belongs to topology means we will say that is open. So there exists an open in set in your x such that this x naught belongs to that open set. And one more condition is that f of u is contained in v that you took here. Your f of u should be contained inside this. So this is the definition of continuity. I repeat, we will say that in topological space, we will say that x and y or x t and yu two topological spaces. Then we will say that a function from x to y is said to be continuous at a point here x naught, means you consider f of x naught and take an element from the script u, that means an open set which contain your f of x naught, right? So this is your b. Then there should exist a u. Here I can find a u in my topology. Some u belongs to t. Here v belongs to u. Then correspond to this v, I can find a u belongs to t such that what's the condition? Which containing x naught, and next condition is f of u should be contained in v. That is, this whole image should lie inside your v, right? So this is the definition of continuity in topology. Hope you understood. So we will say that f is continuous in a topological space from x to y if you're having a function f, and we will say that f is continuous at a point x naught whenever you find an open set in your y which containing f of x naught. There should exist an open set in your t such that condition is f of u should contain inside your v. Now we are having some proposition here. 3.2 proposition. Proposition. The following statements are equivalent. The following statements are equivalent. First one, f is continuous. F is continuous at a point x naught. Second one, the inverse image under f of every neighborhood of of every neighborhood of f of x naught in Y is a neighborhood of x naught in X. And third one, for for every subset a subset of x naught belongs to a closure implies f of x naught belongs to f of a closure. And fourth one, for every subset a subset of x naught delta a implies f of x naught delta f of a. It's nothing but nearness relation. Nearness relation. Delta represent nearness relation. Okay. So these are going to be the equivalence condition for a function f to be continuous at a point x naught. So what is the first one? F is continuous at x naught. Second one, the inverse image under f of every neighborhood of f of x naught in Y is a neighborhood of x naught in X. So very easy, right? Let us see how we can prove it. So we will prove 1 implies 2. Proof. We will prove 1 implies 2. For that, what we want to assume? F is continuous at x naught. Suppose the function f is continuous at x naught. So we have assumed that f is continuous at the point x naught. Now what do we want to prove? We want to prove every neighborhood of f of x naught, inverse image under every neighborhood of f of x naught in Y is a neighborhood of x naught in X. That means we want to prove we are having here x, here you are having y, here we got f of x naught. Take a neighborhood of f of x naught, find its inverse image. From here to here f means here to here you will get f inverse. You find f inverse. Now if that f inverse is resulting here a neighborhood of x naught, then we will say that the function is continuous, that we want to prove. So suppose f is continuous at x naught. Let capital N be a neighborhood of f of x naught. So we have considered a neighborhood here in Y. Then there is an open set. Then there is an open set V in Y such that f of x naught belongs to V and V is contained in N. F of x naught belongs to V and V is contained in N. So there is an open set V because we have taken this as a neighborhood. So neighborhood means neighborhood of x naught means there should exist an open set which containing x naught and which completely contain inside your set N, right? So there is an open set V in Y such that f of x naught belongs to V and V is contained in N. Since f is continuous at x naught, since f is continuous at x naught, there is an open set okay x naught since f is continuous at the point x naught we have assumed, right? Since f is continuous at the point x naught, there is an open set you can say u in x such that this x naught belongs to u and its image f of u is contained in V because V is going to be a neighborhood of f of x naught. So this implies my x naught belongs to u which is contained in f inverse of V, right, from this, and which is contained in f inverse of n because V is contained in n. So f inverse of n. Thus this means f inverse of n, inside that we should find an open set V, right? Sorry, U, right? So f inverse of n is a neighborhood of x naught. This thing we want to prove. Hence 2. So we have proved 1 implies 2. Next we will prove 2 implies 3. That is, every neighborhood of f of x naught, when you took its inverse image, it is a neighborhood in of x naught that we are assuming. And now we will prove that it's going to be the third one. For every subset A subset of x naught belongs to A closure implies f of x naught belongs to f of A closure. That was the third condition. See, we will assume this second one and we will prove the third one. For every subset A subset of x and x naught belongs to A closure implies f of x naught belongs to f of A closure. That's the thing we want to prove. So 2 implies 3. Suppose x naught belongs to A closure where A subset of x. Suppose x naught belongs to A closure where A subset of x. If f of x naught does not belongs to f of A closure, what will happen? This should belongs to complement of this. Then by theorem 2.10, what we are having? There should exist at least one neighborhood of f of x naught which cannot have intersection with f of a, right? There is a neighborhood. There is a neighborhood n of f of x naught such that this f of a intersection with n is empty, right? This means that, or this implies, f inverse of f of a, f inverse of f of a intersection with f inverse of n is empty, right? F inverse of f of a intersection with f inverse of n is empty. Hence, a, this is a intersection f inverse of a. So I have used two types of f. You should understand both are same. This f and this f are the same. I unknowingly used the different f. Okay, let me correct it. So f inverse of this, f inverse of this, that is a intersection f inverse of not a, n it should be, right? F inverse of n is empty since a is contained in f inverse of f of a. But by property 2, but by property 2, every neighborhood of f of x naught, right? To f inverse of, oh, again f inverse of n is a neighborhood of x naught, and so a intersection f inverse f inverse of n cannot be empty, right? Since at least it should contain x naught, right? Cannot be empty since x naught belongs to a closure. Since x naught belongs to a closure, then f of x naught belongs to f of a whole closure. So need of since therefore x naught belongs to a closure, then f of x naught belongs to f of a closure. So we have proved 2 implies 3. Next we will prove 3 implies 4. 3 implies 4. This is immediate since take condition 3 and 4. See, condition 3 is for every subset A subset of X and X naught belongs to A closure, we want to prove f of X naught belongs to f of A closure. Assuming this, what we want to prove? A del X naught delta A, that is X naught is near to A. So when you are assuming this belongs to X naught means exactly X naught is near to A. What we want to prove? F of X naught is near to f of a. That's the meaning of this, right? So this part is very immediate one. So 3 implies 4. This is immediate. Immediate since the nearness relation corresponding to a topology, nearness relation corresponding to a topology is defined by saying that a point is near a set if and only if it is in the closure of that set. It is the closure of that set. So by definition itself, this nearness relation says that whenever A is near to a set X, means A should belongs to A closure. Okay, so this follows very immediately. Now we will prove 3 implies 1. Then we will get all the equivalence condition. So 3 implies 1. 3 means if X belongs to A closure, then f of X belongs to f of A closure. We will assume that and we will prove that f is continuous. So 3 implies 1. Let V be an open set containing f of x naught. Let A equal to x minus of f inverse of V. A equal to x minus f inverse of V, which implies this is nothing but f inverse of y minus V. Then f of A, f inverse of this, then f of A means f of f inverse of y minus V. So f of A is contained in y minus V. Now, therefore, when you are finding f of A or closure, this should contain in y minus V. What's the reason? Since V is open, y minus V is closed. So since y minus V is closed, so we are having f of A closure is contained in y minus V. Now f of x naught does not belongs to f of x naught does not belongs to f of A closure. Hence, x naught does not belongs to A closure by condition 3, right? So x naught does not belongs to f of A closure, then x naught does not belongs to A closure. Hence, there is a neighborhood. Hence, there is a neighborhood n of x naught such that This neighborhood intersection with the A is empty set such that A intersection this set neighborhood is empty. Then clearly, then clearly, f of n is contained in V because it's having intersection as empty. Now, what was your V? See, V be an open set containing f of x naught, right? So here we are having f of n is contained in V because f of n means we are having, see, this is contained in y minus v, right? So this quantity is contained in v. Then clearly f of n is contained in v. Now take u equal to interior of v. V was open set, and we take, sorry, interior of n. You take interior of n. Sorry, interior of n. Now this will give you the open set. Okay, so hope you understood all the concept. So I'm winding up today's session here. Today we have discussed only the definition of continuity and for equivalence condition for function to be continuous at a point x naught. Okay, so be thorough with this concept. With this concept only, we are moving further to the depth of this chapter. So when you find any difficulty in capturing this concept, please stop me and ask me wherever you are finding doubt. Clear it off, then we will move to next topics. Okay. Thank you for your patient listening. Thank you.